Hello again, we are carrying on looking at ionisation energy, but again we're going to start this wee video with a starter activity again. So what you want to do is pause your video and write down your definition for first ionisation energy and also an equation for the first ionisation energy of sodium and a second equation for the first ionisation energy of chlorine. Okay, so on the wee blackboard, we've got a definition for first ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gas phase. Now this is an important wee sort of definition. Just go and get that lodged up in your head. Write it out 20 times or whatever it takes so that you can get that just spot on, getting the important points of it being in the gas phase. You're removing 1 mole of electrons of 1 mole from 1 mole of these gaseous atoms. Okay, for our first ionisation energy equations, for sodium, you're wanting to start with sodium, but remember in the gas phase, sodium is a solid metal at room temperature, but these first ionisation energy values are all for the gas phase. Sodium in the form of a gas turning into sodium 1 positive in the form of a gas plus electron. Okay, so that's removing 1 electron from your atoms in the gas phase. Chlorine though causes a wee bit of a problem for some people, because if they're smart they'll remember, chlorine is Cl2, it's one of our diatomics, and they start working from there. Oh yeah, okay, it's already a gas. But that's not correct, because we've got to remember the first ionisation energy involves removing electrons from gaseous atoms. So we have to start that one again and say, okay, well that should be just Cl by itself. We'll stick with our wee green for our state symbol. Chlorine, atoms in the gas phase turning into chlorine positive ions, but still in the gas phase, and our wee electron. So that's our equation for the first ionisation energy of chlorine. So today we're going to be talking about the second and the third, and there's a fourth and a fifth ionisation energy as well. We're all hopefully now clear what we mean by the first ionisation energy, removing 1 electron from a mole of atoms in the gas phase. So the second, people sometimes get a little bit confused and they think, oh well, the first is taking away 1, the second will be taking away 2, but no, it's the second ionisation energy, it's taking away the second electron. So rather than starting with atoms, this time we're starting with already 1 positive ions. So we're talking about ions in the gas phase, but removing a further electron. So what's that going to look like? That's going to give you an Na2 positive ion and an electron, and that remains in the gas phase. So no prizes for working out then. The third ionisation energy will be taking away the third electron. So you're already starting with a 2 positive ion. Similarly, Na2 positive in the gas phase, turning into Na3 positive in the gas phase, and an electron. Now, in our data booklet, we've got sort of columns and columns of data about all these things, and we're going to take a wee look at some of these and see if we can spot anything and then account for it. So I want us to have a wee look at some of the first, second and so on ionisation energies for some of the elements. We'll just start with period 3 rather, sodium, magnesium, aluminium. We'll look just now at magnesium first of all. Removing the first electron requires 738 kilojoules per mole of atoms. Keep on going. The second one is 1451, but then you've got really quite a big jump to removing the third electron. Okay, we'll look at aluminium underneath it. 578 for the first, 1817 for the second, 2745. So not a huge jump going to the third, but if you look at the fourth for aluminium, that's huge. That's up to 11,577. So we're going to rethink if we can work out what could account for those big jumps that we're seeing at different places. So on the board here on the top, I've got magnesium and its electron arrangements. 2 in the first shell, 8 in the second shell, 2 in the third shell. If we remove 1 electron, we're talking about the first ionisation energy here. That's what this changes. First, ionization energy. We're taking away one of these two electrons to leave you with the electron arrangement 2, 8, 1. If we take away that though, that electron in the second ionization energy, that's giving us this arrangement, 2 in the first shell and then 8 in the second shell. This is where the big jump is for magnesium, for the third ionization energy. Why would that one be so big? Well, look what you're doing here. You're going to a full stable shell that's now quite close to the nucleus. It's not far away like that single electron here was. That's now closer to the nucleus. So you've got this full stable shell that's close to the nucleus, and you're trying to remove an electron from that. So it's no wonder that that value is absolutely huge. Third ionization energy for magnesium is 7,733. So really pretty huge. So if we look at potassium and make a wee prediction, we know potassium's electron arrangement is 2, 8, 8, 1. It's a group 1 element. It's got 1 electron in the outer shell. If we remove that first electron in the first ionization energy, you'd be taking that down to 2, 8, 8. But if you're going to carry out the second ionization energy and remove the second electron from now this closer to the nucleus shell, we saw before that requires a huge amount of energy. And sure enough, if you look in the data booklet, the value for the first ionization energy of potassium is 419, but it's 3052 for the second. So this concept is quite a commonly asked exam question, and you'll see some examples in the questions I'm going to get you to do today.